In this lecture, we provide quantitative approval of those observations that have been made qualitatively in the previous lecture. And also we derive from general theory of relativity some effects which are approved by classical experiments. To do that, we find the geodesics in Schwarzschild spacetime, in that which was found in the previous lectures. And a convenient way of finding geodesics is to use conservation laws, to use integrals of motion. Now we will provide the integrals of motion for the motion of particles in Schwarzschild spacetime. Well, let us start from a generic observation and explain how to find conservation laws. As we have explained in one of the previous lectures, under the infinitesimal coordinate transformation, which is like this, metric tensor transforms as follows. Plus covariant derivative, epsilon mu, and symmetrized over the indices of x. This notation was introduced in one of the previous lectures, so it's symmetrized covariant derivative. So if for some transformation epsilon, for some vector epsilon nu, which we will denote k nu, the metric doesn't change under the coordinate transformation, doesn't change at all. It means that d mu k nu is equals to, which is by definition is d mu k nu plus d nu k mu. So if k mu is such that this is equal to 0, then the metric doesn't change. And such a k is called killing vector. Killing vector. So for example, for the Schwarzschild spacetime, which has the metric ds squared, which is 1 plus r minus rg divided by r dt squared minus dr squared 1 minus rg over r minus r squared d omega squared. As you can see, this metric doesn't change if we make time translation. And if we, because this is independent of phi, because this is a d theta squared plus sine squared theta d phi squared. So metric is not dependent on time and is not dependent on phi. So the components of the metric are not dependent on these things. So the metric is invariant under such transformations. I don't know, for arbitrary a and b. These are exactly the killing vectors, which I explained in a different way just by looking at the metric. So they are seen explicitly in this metric. So at least we have these killing vectors. And they, in the notation that k mu has the following coordinates, kt, kr, k theta, and k phi. This one corresponds to k mu equal to 1, 0, 0, 0, while this one corresponds to k mu equals 0, 0, 0, 1. So these are the killing vectors. At least we have these killing vectors in the Schwarzschild spacetime. They are explicit in this form of the metric. Explicit in this form of the metric. And let us see that the presence of the killing vectors leads to conservation laws. For example, consider a particle moving along z mu of s, which is a curve, which has a world line z mu of s. Correspondingly, its velocity for vector is dz mu over ds. Now, consider the following combination, k mu times u mu. And let us take its derivative, d over ds which is a proper time, of k mu times u mu. Then this is just d nu of k mu times u mu dz nu over ds. Well, this is just u nu. And now we take derivative of this. Derivative of this is the following. So by Leibniz rule, so first of all we have this u nu, but then we use Leibniz rule, which means that we get k mu times d nu u mu. So we apply to this thing, plus we apply to this vector, which is u nu u mu times d nu k mu. Now, let us continue and represent this as k mu u nu d nu u mu. Plus, remember that this is, one can see that this is symmetric under the exchange of indices u and mu, so this can be represented as 1/2 u mu u nu u mu times d nu k mu symmetrized. Means like this, represent like this. So now one can see that if the motion, if this thing is geodesic, so then the motion goes along the geodesic. This is 0, because this is the equation for the geodesic. This thing is equal to 0. And if k is killing vector, then this is also 0. As a result, we obtain the following conservation law. So this quantity doesn't change, doesn't depend on proper time for the motion along the geodetic. So this gives us a conservation law. So our goal is achieved. We have shown that if there is a killing vector in a space-time, then that generically leads to conservation law. Now we're going to consider these conservation laws for the Schwarzschild space-time in greater detail.